our Let's Talk to an Expert series, an exciting initiative by Xperimentor. At Xperimentor, we believe that science education should be engaging and evoke curiosity in children. Our goal is to inspire young minds through hands on, inquiry based learning. In this series, we bring you talks by experts from various scientific fields. We believe these sessions will spark curiosity and provide a unique opportunity for children to engage with directly to the experts. Before we begin, we have few instructions for the session. This session is designed by Ram Mohan sir to be engaging, so feel free to be participate actively. To avoid audio disturbance, we request all of you to mute yourself during the session. If you have anything to ask or contribute, please use the raise your hand option. Ram Mohan sir will be asking questions throughout the session. So please use the chat box to drop your responses. If you have any questions, please post them in the chat box. We'll try our best to address the questions. This session will be recorded and shared on our social media handles. So today we are exploring the wonders of the night sky, and we have an exciting guest to guide us. Joining us is Ram Mohan, a software architect at HCL Tech Bangalore, with an unshakable passion of unraveling the mysteries of the cosmos. An electronic engineer and MBA by qualification, he has pursued advanced studies in astronomy, astrophysics, cosmology alongside Indian and Vedic astronomy. His integrity shines through his hands-on approach. He has designed and built 4 radio telescopes and used his rooftop observatory to capture breathtaking astrophotography. So, sir, welcome to you, and we are really excited. So, floor is all yours.
Good evening and welcome. Thank you so much, Sarah Parna, for all the nice introduction, and thank you, Experimenter, for this initiative, and my good friend Yamuna as well. So the way we are going as much interactive as possible, please feel free to keep asking questions either through the chat or even you can unmute yourself and ask. There's nothing like you can ask at the end or something. There are already some questions which are submitted that I will try to take it up during the session, or some of it do get answered during the session, or some of it we can readdress that at the end of this session. And that's how I would like to run, and let it be as much as possible interactive. With that, what I'll try to do is that I'll try to switch off my video and try to share my screen. That will be the best way possible, because many of my presentations does have videos and some pictures, and most of these pictures are high resolution, though I have tried to compress them. But when I try to post them on the web or transmit them like this through Google Chat, at times it gets slower. So with that, thank you and welcome once again, and let me just start sharing my screen. I'll switch off my video. Am I audible? Is it clear? Is it all good?
Yes, sir, you're audible.
Okay, great. Thank you. Okay, let's switch. So let me know if you're able to see the whole palette of the slide. Is it all visible? It's fully visible, clear?
Yes, sir, it is.
Okay, great. Thank you. So the way we are going to do this is that we are going to take up certain basic topics today, and we are starting with an introduction to astronomy and stargazing. As such, this is a topic which runs for months and weeks, and it's an ongoing topic. And I'll try to do the introduction part, and we'll see how it goes and if the series needs to continue. With that, I'll just go to the next slide. So what we are trying to do today is try to give a very brief history of astronomy, and then we'll try to understand why we need to study this subject, and then we will try to get some idea of what Indian astronomy and what it means, and how they have our ancients have studied the skies. And then we will start getting into basic observational astronomy, how to really see the skies, and what are the tools and and all the aids that you require to see the sky and everything. And then we'll just end with a small set of things that I have tried to image from my observatory here in Bangalore. So I'll go to the next slide now. So this is the known universe, right? So this is a picture which shows the known universe, where we'll start going this way and go towards the left. So here is where, in the modern cosmology, there is the Big Bang happened, and then there was a time after Big Bang. There was nothingness, and then there started, all these atoms started coming together, molecules started coming together, and some form of matter started clumping. And then we started seeing first strands of stars appearing. And from then on, if you start seeing, what all do we have? We have superclusters, galaxy clusters, uh, we have spiral galaxies, irregular galaxies, dwarf galaxies, many different kinds of galaxies. Then we have different kinds of stars. So stars are of various sizes, they come in different colors. And then we have objects like supernova and the remnants of supernova. Then we have black holes, pulsars, neutron stars, magnetars. And then we have other uh, other objects, like we have nebulae. Nebulae are all those clouds, from the interstellar clouds from which new stars are born. Most of the time we will see them as well. And then we have a few other things, and we start coming now into the solar system, where we have the sun itself. Then we have all the planets. Around the planets we have a lot of moons. Most of the planets do have moons. And then we have our own moon, which is Luna. And then there are so many other phenomena which keeps happening in the universe. Something like fast radio bursts. And then there's still unknown phenomena called as the dark matter, the dark energy, many of these things. A lot of studies are still going on them. So this is how the universe that we know as of today, as of now. But once we know all of them, and what is the method to study, so that is what astronomy does. It's what is astronomy? It's an observational science. We will come to this topic called as observational science. It's a very observational science, and it involves methodical study of celestial objects and phenomena. That's the definition of astronomy. So now we'll start getting into the history of astronomy next. So I think it's very natural that a man who has been walking on the earth, they have been always been kind of awe of the night sky, and they have always been curious. So with that curiosity, they started to start looking at it, and they start seeing that some dots keep changing in the sky, some dots remain as they are, and all that. That's the first step which the men took, or our own history of civilizations. If you see, even in the caves, they have etched, or they have done some paintings of what they have seen in the skies or recorded. So that curiosity still continues among all of us. And if you see the history of astronomy, it's the oldest of natural sciences. So, and it's also called as the mother of all sciences. Now, when we call as mother of all sciences, here it includes mathematics, it includes physics, chemistry, biology as well. Now, as we call it as mother of all sciences, it's just that not only Indians, but every other imaginable civilization which has been there on the earth have always been recording the events that they have seen. And that's how we have Babylonians, Greeks, Egyptians, Iranians, Chinese. There are many other civilizations who have watched the skies and recorded what they have seen. And now coming to the recent times, I'm coming to the recent times is around where we have around 200, 300 years, where a lot of science in the physics part and in the mathematics part has also progressed in the modern in the modern parlance. So astronomy has is also become synonymous with astrophysics, and otherwise it was also used in celestial navigation. Many different fields they were using it. Now coming to the Indian astronomy part of it, India has been always in the forefront of astronomical studies, and the sky has always intrigued the Indians right from the time of Indus Valley civilization, or if we start going towards the Vedic age. So in when we have the four Vedas, and then we have six Vedanga, so which is the auxiliary study of Vedas, are called as Vedangas. Among them, one of them is called as Jyotisha. Jyotisha, Kalpa, Vyakarna, all these are auxiliary studies. Jyotisha, as such, if you take in the these days, what they try to say is that the moment we say Jyotisha, it's most of the time attached to astrology. That's the normal parlance of these existing days. That's not true. If we just even go back and understand the word, where does Jyoti or Jyotisha comes from? Jyoti is nothing but light. Jyotisha is nothing but study of light. So that's the definition of that, which means that we should not relate this to astrology. Always, if you go back to the earlier times, Jyotisha always meant study of the celestial systems and mathematics. These two are always taken in the same breath if we go back to some of the olden texts. So Jyotisha is also known as the eye of the Vedas. That's it's been given one of the most premier subjects to be studied as mandatory subjects when people were going into the old Gurukula system of education, because that used to give a vision for them to understand the whole universe and cosmos and everything. So that's why it was called as the eye of the Vedas. Now let's go to the next slide, which just talks about why study astronomy. So this is a saying by Carl Sagan, which is also there as part of his video in Cosmos. It's a series. It's a wonderful series. If people have not seen, they should see that. I think it's also available on YouTube and other places. It's a series on introducing of what is there as part of astronomy itself. Carl Sagan was one of the premier contributors for the Voyager missions in late 1970s and early 80s. So this Voyager spacecraft, which is over here, it's now crossed the edge of the known solar system and drifting into the interstellar medium. So one of the most important pictures was when one of these spacecrafts turned towards the Earth and took a picture just as it was leaving Saturn, and that's the pale blue dot. So that's the picture of this Earth suspended in the sunbeam. So that's how Carl Sagan tells, and he says that astronomy is a humbling and a character building experience. Reason he says so is when we start exploring the universe, then there are so many things which are much unimaginably larger than us, unimaginably far than us. And when we start looking at those things, when we see Earth, which is just suspended as a small speck of dust in a sunbeam, and it just feels that we are nothing, and we are so tiny. So that's where the humbling part of the experience comes. And character building, that the reason being that is most of the times it takes a lot of effort from the person to pursue this either as a hobby or as a career. It involves a lot of failures. It involves a lot of experimentation. It involves uh, it brings in that kind of uh, personality where you have to start doing a lot of experiments. You sometimes have to be very resourceful to do things yourself and understand. There is nothing in one book which teaches you everything. It's most of the time that you will have to experience it. It's just like swimming. So there's no book which just teaches you how to swim. You just have to jump into water to experience that. That's why it's also called as a character building experience. Now I'll just go to the next slide, which just gives us a very tiny introduction of what Indian astronomy means. Kindly do, if you have questions, do stop me and you can ask um, when I'm navigating through the slides. So Indian astronomy, as I was telling you, has got a very, very long history. So the one of the oldest known astronomical texts ever in the world is called as Vedanga Jyotisha. So recently, Vedanga Jyotisha has been kind of dated approximately to 1400 to 1500 BCE. So this might be the time. There is a lot new parallel research which is going on. So many other texts which are there in India, which might be either contemporary of this one or it might even predate. So we will talk about that when we get time. So it means that India has got a very long history of observing the cosmos and observing the celestial bodies and recording all of their movements and keeping data of them. Now, Vedanga Jyotisha as such has been derived from the Rig Veda and the Yajurveda, certain verses. So in Rig Veda, we have 36 verses which have been borrowed, and from Yajurveda, we have 43 verses which have been borrowed. So when we start reading some of the portions, I'm not going to explain the whole part. I'm just going to give you one portion here which tells us that in a year, there are 366 days in a year, and we have 6 seasons. Rutus in Sanskrit means seasons. 2 ayanas are called as sun's courses, or we call it as today the solstice. And then we have the 12 solar months, and then 5 years makes a yuga. So just imagine that somebody uh, at almost 1500 BCE was able to calculate so clearly how many days are there in a year. It's a very, very difficult calculation to do, by the way. We'll come to that in a minute why it is difficult. Now, the way Indians looked at the whole astronomy was from a very practical point of view. They were not trying to gain any, oh, where is a black hole? No, that's not what their idea was. Their idea was very simple. They wanted to do few fundamental things like determination of direction, place, and time. So we call this in Sanskrit as Dik, Desha, Kala, Nirnayaha. So, or it is called as Dik, Desha, Kala, Nirnaya Shastra. Astronomy or Jyotisha was a study of this, and it is also telling here, where I've just marked it in red here, it is a subject which teaches us how to determine the time, place, and direction. Dik, Desha, and Kala. Dik is direction, Desha is the place. Here, Desha doesn't mean a nation the way we use in Sanskrit. It is the place. If you are, say, for example, you're staying in some area in Bangalore, that is also a place. A place where your home is located, that is called as a place. How do you find out latitude, longitude for all that? So that is the place. And Kala, how do you find out what is the time? Now, that is where they say that by observing the motion of celestial bodies, we get an idea of time itself. So this is one of the earliest ways that they started determining time. I've just given a few things here in the same. This is a Sanskrit shloka called as Yathashikha Mayurana Nagana Maniyo Yatha Tadvad Vedanga Shastranam Jyotisham Muvardhini Sthitam, which means that like it's written here in English, which you can read like the comb on the head of the peacock. It's just the crown on the head of the peacock or a jewel on the head of the snake. The scientific composition of astronomy occupies top of all the 6 annexure of Vedas. That's what how much importance it has been given even in the earlier times. Now, just give you a couple of things. One is, how were they measuring time? Fundamental measurement of time is that, like we have in most of the Indian languages, starts with e, and this is how it starts. So, is the smaller matra, is the Gurvakshara or the larger matra, the longer matra. So, 5 of that longer matras is equal to 1 kastha. So that is how they started measuring time, and it is also sometimes connected to the time that you take for the eyelid to close and open. That's also kind of equated. There are many other parallel this kind of examples which are present even in the scriptures. So that way they were able to go to the smaller portions of time, and in fact they are going much smaller in through T and all that, which is much, much, much smaller portions of time. And then they are going to larger portions of measuring days and months and years and everything. And what were the tools that they were using to measure time when they were not able? This is a sundial, by the way. This is one of the earlier tools. And then they were also using something called as clepsydra, or a water clock. You see, there's a vessel of water here, and they have a tiny vessel and a larger vessel. And the tiny vessel, if you see here, observe, there's a tiny hole, a small hole, through which water seeps into the vessel, and then this whole smaller vessel drowns into the larger vessel. The time it takes to drown is exactly measured most of the time as part of nadikas. So one nadika is most of the it's equal to 24 minutes. So then that's how we get one mahurta. So there is a series of calculations. So they were using these kinds of devices to measure time. Like, it's not like what we know today as the clock. Okay, and we'll start getting into the next part, which is a bit more of the observational things. I just want to stop here and ask the younger friends if they can tell that how do you say how much is 1 hour? What is the measurement of 1 hour or half an hour? How did this fundamental measurement come from? Anybody? You can unmute yourself and tell. How do you measure a minute or an hour or 30 minutes? How do you measure that? Imagine there is no clocks, nothing at all. No one? Okay. So let me just give you how this started.
We have one response here.
Yeah, sure.
Ashwin Guha says that 1 hour is 1/24th of time between two sunrises / sunsets.
Yeah, you can call it of that way, but in practical method of observing, it is like this. You can look at the sunrise, say it happens at 6 a.m. in the morning. If you look at 7 a.m., the sun would have moved at some from point A to point B in this sky. So the angle that it is going to take to get into an hour is constant. That means that it is going to traverse from tip to tip, 6 a.m. if it sets in the west at 6 p.m. So we have 12 hours there, and if we understand that it comes back again the next day, and if you assume that it is going to be 360 degrees, so 12 hours means every 1 hour it is going to take or move 15 degrees in the sky. So this is how, irrespective whether the sun or if you look at any star, it starts moving. That means that relatively Earth is spinning on its own orbit, and that is making either the sun or the star spin. So that's how they over a period of time they understood, and that is how we call it as hora in Sanskrit, or hour now in English. Okay. So ahoratra is nothing but the whole night and day, one sidereal day, and if you take that as, that is called as ahoratra. So from that response, 1/24 of it is correct. So, but otherwise, that's how for us, even the idea to measure time, or even to understand time, the one of the first ways, or the whole idea came from looking at the skies. So that's how practical it is, and even today we do the same, and that's how civilizations have used as well. Now, if you start looking at this is the sun, a picture of the sun, and if you assume that, if you look at this, this is the elliptical orbit on which the Earth takes to go around the sun, and and every dot here signifies a day. So if you imagine every dot in an elliptical orbit, Earth needs to move. How much degree do we know? How much degree does this take when we say an elliptical orbit? It's okay, it's almost 4 degrees. So because if you imagine that it needs to move the same amount of degrees, like if 360 degrees if it has to move, and it takes almost 1 degree a day, then you should get 360 days in a year. That's not what it is. It's much more than that. So since we are moving in an elliptical orbit around the sun. So, and when we start observing the sun every day, as most of the textbooks do say that sun rises in the east and sets in the west. Now, if you start observing the sunset itself, what will happen is the sun doesn't rise at the same place in the east every day. This is a picture of an actual picture taken by one of the people in Hong Kong. What he has done is that at every 7:30 a.m. in the morning in 2014, he just placed a camera on top of his balcony and started capturing the sun, which is rising from here. To see what a diagram this draws, as you can see that the sun takes or we when we go around the sun, and how we see this diagram is called as analemma. So here is 30th September. Now that is where we have the equinoctial points, and then this is the solstical points. We have the summer solstice here, and then we have the winter solstice here, and then these are the solstice points, and this is the a kind of a geometrical pattern that the sun creates, and every if you look at the equinox point somewhere here, and from the left we go 23 degrees, and then in the right we go 23 degrees, 23.4. It's just like that. That's because of the Earth's tilt. Sun goes like this and it comes like this. So that's how the appearances are, since we are moving in an Earth is tilted and then it's going around the sun, and that's how Earth traces. But we, as an observer from Earth, tend to see this picture like this. So this is how you can start understanding the fundamental nature of measurement of time came from here. The inspiration came from here. And this is called as a shankhu or a gnomon. This is part of this is a very simple instrument which has been part of Indian astronomy for years and years now. They used to use this stick on the ground and draw a circle around it, and just with the sun's shadow you can find out east, west, north, and south. The celestial east, west, north, and south, as accurate as possible. In fact, the accuracy of this one, if you do it through this method, it can go up to 3 to 4 decimal points, and it is much more accurate than a GPS truncation. So these are actual pictures of what I have done on my rooftop. And this gives you the actual east, west, north, south. By the way, if you use a compass, the magnetic north versus the celestial north is always different. So in terms of the error, the magnetic north versus celestial north is 1.96 degrees here from Bangalore. 1.96 degrees is a huge, huge, huge error from astronomical point of view. You'll be seeing some other object when you want to see something else. So that's the level of accuracy that you require when you start actually looking through the telescope and recording images and everything. Okay. So this is the experiment that I have done, and this is the markings that I have done, and it's wonderful. Sometime we can talk about this probably. And this is an actual picture of the analemma from Bangalore simulated. Uh, and what is the degree? You see, if you just imagine this a straight line when you draw here, and when you imagine uh, this point between these 2 points, if you just imagine what will be the angle between these 2 points, it will be actually 12.59 degrees. That is how Bangalore's latitude is. So you can find out the latitude of a place by observing when in the INR stages of the sun, what is the farthest point that the Earth, of the sun takes during its summer solstice. These are fundamental calculations that you can do even today and understand what is your current latitude. Where are you in the curvature of the Earth? So this is analemma. Now let's start going into basic observational uh, aids that we require when we start exploring the night sky. If I'm going too fast, do pause me, let me know, or if you have questions as such. Now, what we need to do is that as we start observing the night sky, uh, we do get confused because the sky is a very large area. If we go to a very clear place, there will be so many stars, and we don't know where to start from. So that's how the first part of the naked eye comes. Then we generally use a compass just to find out, okay, where are we looking at, which direction, unless we know it, whether it is east or west or north or south. And then we have something called as planisphere, or this kind of star dials. Just by looking and you can you can you can use these star dials to find out today at around, say now it is 6:40, where if I start looking the sky at 6:40 a.m. p.m. sorry, where are the stars and what stars can I see, what constellations can I see. It's a very simple device, and you can use this to find out what all constellations or stars can you see at a given point of time in a given month or a given day. It's that simple. So this is what it is. And then you need certain aids to also make sure that you can see or resolve a particular object very clearly. That's where you start using the binoculars. A pair of binoculars always is a good start to observe the sky, to identify basic objects in the sky, and then get into telescopes and buying or investing or any such things. So this is the best way to start. First, start with naked eye, understand the constellations, understand how the patterns of these constellations are, and then start resolving individual objects in the constellations, and then you can start in exploring the whole sky. So that's the normal route which is recommended. And then these days, before I go into telescopes, you have softwares, planetary software like Stellarium, Cartesius, and everything. So just I want to pause there and ask if you can unmute and ask, is anybody here using any of the software uh, to see objects or to locate objects in the sky? You can unmute and say, I am unable to read the chat window, just in case if you are typing. Okay, if you are not using, you can always download Stellarium and Cartesius, or there are many such things. All these which I am trying to tell, they are all freeware and they are all open source, no licenses required. And you can download them and start using them. I'll try, if I do have time, I will just show you a small glimpse of how they look as well. We'll see how it goes today.
So Yamuna ma'am have raised her hand.
Yeah.
Okay. The app, the phone app, Sky Map, gives
Yeah.
a good view of the celestial objects in the sky. So I generally use that to locate the constellations or the planets that I want to check it out.
Oh, it's a good app, no doubt. But my suggestion or recommendation, who wants to get into the next level, is not to use the phone apps.
Okay.
Okay, the reason being to first is these phone apps work on the internal compass of the phones, and most of the time they are not that alike. Second, the phone apps will not give you the kind of data when you want, or the richness of the content, what the standalone apps which are available on the laptop or desktop computers. It gives you, you can do an independent study sitting at home, or to understand how the sky looks before you say in the late in the evening, 4 p.m. if you go and do that, and then at around 6:30 when the sky gets darker, you can go out and see, and then you will be able to identify them. So you can correlate. But the phone apps, yeah, it gives you a smaller amount of a window. That's the only challenge.
Okay.
Okay. Now let's get into the next topic, which is understanding the types of telescopes. Are anybody here seen or observed any celestial objects using telescope? If yes, um, you can yeah, you can unmute and say, or just want to know so that we can understand what is the depth that I need to go in. Okay.
Uh,
I have
I
seen
mean,
Venus and the moon using a telescope.
Excellent, excellent. So, do you remember what kind of telescope you used?
I think I remember it was a very big one.
Very big. Okay, good. So now telescopes as such come in various types. So the one of the most of the time when we start using a telescope which has got lenses in it. So there might be two lenses or more than two lenses. It depends upon the design. And light enters through the larger lens, and then it gets focused and where the eyepiece is going to be is here. There's a small lens, and the light focuses onto a focal plane or a focal point, and this magnifies the object further, and that's how we start seeing. So this kind of a telescope is called as a refracting telescope. Refracting, it works on the principle of lenses refracting. And then we have another kind of a telescope called as reflecting. Um, so this is also known as Newtonian telescopes, because Isaac Newton was one of the inventors of this. It works very simple way. You have a large mirror, which is a kind of a hyperbolic or parabolic mirror, and then light falls on this mirror. That means the object falls on this mirror. It gets further reflected into a tinier mirror here, which is placed at an angle. And then you have a small eyepiece lens, which further magnifies this object. So this kind of a telescope is called as reflecting telescope. Now, in the earlier 1800s, 1700s, most of the telescopes used to be refracting. So you hardly find refracting telescopes today in any large observatories. They all use a new design called as a Cassegrain design or a hybrid design. So even Hubble Space Telescope James Webb Space Telescope, all use these designs today, which are up there in the sky and observing the cosmos. They have a hyperbolic mirror here, and then you have another mirror. The object of which you are observing, or the reflection of that, falls on this mirror here, the larger mirror, and then it gets reflected onto this tiny mirror, and then you can put a camera or an eyepiece or any other equipment to observe the object, or to see this much further. Now, this is the kind of telescope which is called as hybrid or Cassegrain. This specific design is called as Ritchie-Crichton. This is what I also own, one of them, and that is also one of the telescopes that I use for taking pictures. That's about telescopes. That's a basic introduction. Now let's start understanding a bit about the sky itself. Now, when we start looking at the sky, comparing that, assume that it's a clear winter night and all that, and you are in a village far off Bangalore versus what you are in Bangalore city, you have in the suburban skies or the inner city skies. So when you get to an excellent dark location far off in some village, you will see a lot more stars than what you see in here in the city. Reason being very simple. One is that we have a lot more light pollution in the cities. Then we have fog, haze, because most of the buildings are close by. And then you have smog as well. Smog is a combination of pollution coming from various other sources, like even what is on the road. When we have a lot of vehicles on the road, they also leave out a lot of gases, exhaust gases. Plus, most of our roads are tarred or tarmac, so that also absorbs a lot of heat and starts radiating upwards towards the sky. All these starts making the sky look blur. So there is something called as the Bortle scale. Bortle scale is what is generally referred by astronomers to find out how dark is your sky. So excellent dark sky means Bortle scale 1. It goes the other way around. So when you have very horrible skies, like what you see in Bangalore, it's around 8 or 9. So one of the worst skies that you can imagine. So this is the Bortle scale. So it's a good reference to know that, okay, this is what you always refer to when you start saying that where you are looking from. What is your sky scale? Generally, that's how it comes. Most of the pictures are rated that way. Then you need to understand few other things as part of the basic observation. You need to know the movement of the Earth. All these are part of textbooks, but still, it's good to understand a bit more depth in this. So how much does Earth rotate on its own axis? So you can go back and read about all this. Then what is meant by an ecliptic? Ecliptic is a imaginary path in the sky which the sun traces over the year. So that's the path that the sun traces, and most of the solar system objects, the planets, are found in this, and they move behind the patterns of constellations called as zodiacs. So we all know that what is meant by zodiac. So this is called as zodiac signs. We have Capricorn, Sagittarius, Scorpius. All this you can see them actually in the sky, and when Earth is going around the sun, it traces this path, and it appears as though sun is taking. It looks like sun is traversing this. Or when you look at the moon, also you get the same idea. So that is the ecliptic. By the way, all this planet parade thing is going on right now. Most of the time, all the solar system objects, most of the planets always are there in the ecliptic. It's not that they go away from this line. It's not that planets are all arranged in a same line and they look like they are standing in a queue. That's what is shown in the pictures. That's not how they are. They are spread across a very large area within the sky. It so happens because of their orbital motions, some of those planets come to each other, and they try to start appearing nearby when we see from Earth. So that kind of uh, observations, when we do call, it's called as conjunctions, and these do occur quite frequently. It's not that rare. So we start appreciating what is the hype versus what is reality. I just started trying to tell that. Then there is the celestial sphere. We need to understand, okay, Earth is tilted 23.5 degrees, and we see the pole star exactly at the almost at the pole of the Earth. So we have the north celestial pole, and then we have the south celestial pole of the Earth. The sky also extends this way. And then we have the equinoxes, the hour circles. I was trying to tell you that if you start counting 0 to 24, 1/24th of an hour, so the time taken to traverse this is 1 hour, and the angle here, if you measure, it is 15 degrees. So that's how it's all the fundamental things. And then we need to know what is meant by a meridian. Meridian is nothing but, what's the date line that we use today. So these are all things that we have to know. And next, let me just go to the star magnitude. Star magnitude is nothing but, some star starts appearing to be much brighter than the other stars. And how do we start grading which star is brighter or which object is dimmer? If you magnitude system, if we start understanding this, it's more of a logarithmic scale system. So if we understand sun's magnitude or brightness, it is -27. So it means that, as it starts moving in the negative number scale, the object appears to be much more brighter. The full moon is around 16 -16 uh, magnitude. And when you start looking at one of the brightest stars in the sky, Sirius, it's a magnitude of -1.6. So on. Then you have a lot many other stars that you can see or observe. So each one of them is a magnitude. You can see what is the relative brightness. Sirius is around, if you just take this, 900 times much more brighter than the other star, which is Canopus. So this is a logarithmic scale of volume. Okay, so we need to know about the magnitude system. Then we need to also understand, when we look at the sky, what is the quality of the sky? Is it good or is it bad? Or how do we understand that? We can understand by in a very simple way. When you see that the stars twinkle, that's what they say, right? When the twinkling of the stars, or the rate of twinkling, is too high, it means that the air disturbance is too high. We call it as turbulence in the air. That's too high. It means when you have a high amount of turbulence, you will start seeing fuzzy objects through the telescope, because telescopes generally magnify and show. And if you want to have clarity in your viewing of the object, you need to have stillness in the sky. So it means that the turbulence needs to be less. So that is why we call it as, if there is air disturbance, we call it as seeing is poor. Seeing is a term in astronomy to describe the quality of the sky as well. And when we call it as good seeing, it means that stars shine with a fairly steady light. It's quite steady. There's not much twinkling going on. So just by looking at the sky through your naked eye, we can determine, today, should I really start doing an imaging session or start doing an observing session or not? Because most of the time it so happens, when we start taking pictures of, I'll start showing you some pictures, when we have to complete pictures of certain resolution, it takes days for me in Bangalore. It takes almost 5-6 days to get one good astrophoto. Continuously, I'll have to take it for the whole of the night, one object only, for 3-4 days or 5-6 days. So I have to understand what's the quality of the sky before I start taking pictures. Then you have to avoid certain things. if you have to do some serious observation other than the moon, you should avoid seeing the sky on a full moon. Don't see the any object in the sky which is nearer to the horizon, because the air blanket is very high near the horizon. As it starts going up towards the zenith, the air blanket reduces, and it starts any object that you start seeing which will be much more clearer. Avoid heated rooftops and don't see anything through a window, because window pane will also have a glass and it affects the seeing. That's how we call it. These are few things that we have to do, do's and don'ts. Okay, then we'll start getting into immediate solar system. We need to know all this. These are all already part of many of the textbooks, and it's known that what are all part of the solar system, what objects are present within the solar system, where are the Kuiper belt, and where is the asteroid belt, and so much. It's basic science that we need to understand. Then we need to understand few things like this. Now, here is where we need to understand. I'll just uh, just a second. I'll try to play this video. You see, we have to understand what is the rate at which each of these objects are moving, planets when I mean. So how much, what is the orbital period of each of those planets? Like if you see Jupiter, though being the largest, takes the fastest in its own orbit. It takes around 9 hours, 55 minutes. And then we have Saturn, and then we have the Earth, and that's how it is. So we have to understand what is the tilt angle of each one of these planets and what is the orbital period of this. This is very, very important for us to understand, for us to know, and then we can, then when we observe, we will come to know that what area of a planet are we seeing. So that is why these are important. Next is we have to know that as a standard, there is 88 constellations today. There were many, each one of, I told that there are many civilizations which have been viewing the skies and marking their own constellations in their own ways and everything. But IAU, which stands for International Astronomical Union, has standardized all the constellations now, and the whole sky is divided into 88 known modern Western constellations. So 88 is the constellation names that you have to know, and this is how they look when they are drawn as the patterns in the sky and among the stars. Okay. So I'll just give you the names of this. These are all common information you'll find anywhere on the internet. So this is 88 constellations. Once you understand the constellations and how they pictorially look like, and what kind of, there are primary stars or alpha stars in each one of those constellations. Once you start identifying them, you can just start reading the sky like an atlas, or like what you do when you have a globe in front of you, you can find out what's the pattern of America's map compared to an Africa map, to compared to an India map, to, that's how it, once you just first starting, it might appear difficult, but over a period of time, as you start learning, it becomes easy. And there are also catalogs. I'm just giving you two catalogs called as, one is called as a Messier catalog, another is called as a Caldwell catalog. So these were all in early 1800s, late 1700s, that few people like Charles Messier, they cataloged most of the objects that they saw. And and even today, it is known by these catalog names, like M1 is known as a Crab Nebula. This is the Crab Nebula picture. So these catalogs are good to know, and you can also use internet to download these catalogs for your reference. They're all free, once again, just to know what the number associates with a specific object. And whenever somebody tells that I'm looking at some objects, say like M77, you know that they're looking at a galaxy here, like a pinwheel galaxy, something of that sort. Yeah. So then that's how easy it's much more, and kind of a reference for you to know, and it also tells in which constellation each of these objects are present. So you know eight constellations, and each of these constellations hold any of these objects, sometimes more than one. So you'll get to know about the constellations. With that, I'll start getting into what I try to do. If you have any questions now, you can ask. Any questions?
So we have one question in chat box.
Yeah.
So Rahul Jain asks that he wants to buy a telescope for home use, and his kid is 12-year-old, and they want something which can be used independently by his daughter. So can you recommend something?
Okay, we will talk about buying and investing is a different thing. Okay. I'll try to, we'll see. I'll answer that question one-on-one, or I'll try to answer that in a group later as well. Okay. Let's park that question for a while.
Okay, so Yamuna ma'am have another question dropped in the chat box, that is that the reason water clock used to measure 24 minutes?
Yes.
Yeah.
That is 50 palas of water that you take, and that used to be called as a nadika, which is half of a mahurta. Yeah, which has got many other correlations, but yeah, it's like that.
Okay, so sir, we have also received interesting questions from the student through the registration. So
Yeah, yeah, we will answer that questions. I think some of them are going to get answered in these pictures, and
Okay.
if there are specifics, we will retake those questions once again just after I finish this.
Okay, no problem, sir. Thank you.
Great. Okay, now next, what I'm trying to show is objects as I see, or as I have observed from my observatory. Now, when I say observed or observatory, it's very important. As I told that astronomy is an observational science. You see the sun every day, but if you don't know that in an hour sun traverses 15 degrees, right? That is observation. If you know that, okay, it takes 15 degrees for it to reach point A from what it was previous to point B, it takes 15 degrees, and that 15 degrees is equal to 1 hour. That comes from observation. Seeing is, okay, you see the sunrise and you or sunset and you feel happy. But if you observe, then you'll come to know what else you can do with it. That's the power of observation. And that's why it's called as an observational science. Now, these are pictures that I have tried to take. This is the solar system pictures of, and you can see the sun here, and you can see the sunspots as well. By the way, when you're viewing the sun, it's very important. Never ever see the sun through your naked eyes. Most of the time, you can do that safely during sunrise or sunset, but beyond that, if it gets almost 3 or 4 degrees up in the horizon, sometimes even 5 degrees and beyond, never look at the sun directly. You can always, you will first start feeling the darkness in your eyes and all chances that it can go blind. So never please do that. So we always use a solar filter, and that's how through the telescopes we see the sun and capture these kinds of images. So you can always resolve the sunspots, start measuring the sunspots, understand the solar physics itself. It's a wonderful thing. Then this is Venus, as I saw that on 1st of Jan, Mars, Saturn. You can also see, this is the Saturn's one of the moons of Saturn here, Titan. This is Jupiter. You can also see the various bands of Jupiter, Great Red Spot, and then you have one of the moon, Europa, is casting a shadow on Jupiter. You see, this is the moon here, and this is casting a shadow on Jupiter. You can observe all these phenomena. It's wonderful to see. And this is Uranus, and of course, moon. And this is a picture of a comet. Okay, then you can start understanding what takes an object to be a comet and how different it is from an asteroid. And You can see this comet is moving very fast when it compares to all the stars which are there in the background. The stars are all traced out like this, and the comet is clearer. That means it's moving much faster than the stars in the background. So this is how you see comet, and this is a picture of the Chandrayaan-3 landing spot called as Shiv Shakti point, and this is the point here. By the way, when I point to this point here, this place is almost 2 kilometers in radius. It's not that you can just go and see the spacecraft sitting here through a telescope from the Earth. Impossible, impossible. If somebody is trying to tell you all that, it is just not possible. There is no telescope which is built which can resolve objects of that size on the moon, though it's one of the nearest objects to us sitting here. No, it's not. So this is a rough point here where it is. This point itself is almost 2 kilometers in the square area. So this is how you start. You can start observing them. You can start mapping certain areas, start understanding why these marks are like this on the moon, what made them. It was all made by meteor strikes. We can go into a whole lot of physics just by understanding this, and you can start measuring each one of them by the shadows that is cast, and length of shadows determine what is the size of these. So you can all do a lot of physics just by observing. And then this is a 7-year observation log of Saturn. This is my log. So just you can see what happens in, say, the 2019 when I started taking pictures here. The Saturn's ring tilt was around 24.4 degrees. Now, as it's starting to come to, say, now this is 7th of Jan, so the tilt angle, you can see the tilt angle is changed completely of the ring. Saturn is giving you a different position to see altogether, and the tilt angle is 1.77 degrees. By around May, March, end and May, this will just appear as a straight. Trying to see Saturn, they will not be able to see the Saturn's ring at all for an year and a half now. More than that, it will just appear as a straight line cutting across the planet. So this is where the power of observation comes. You can start observing. With this, you can determine how the Saturn is moving across the sun in its orbit. It is taking a path just like a cyclist does in the velodrome. If you have seen the Olympics, the cyclists go around in a kind of a banked area called as velodrome. If somebody is sitting in the middle, the cyclists just turn, twist, and go. That's how Saturn is moving up, and you can just observe that. Then you start taking pictures, and this is the power of observation. I'll show you another picture. This time it's this is the 6 years observation log of Jupiter. You can see that the whole pattern of the cloud pattern of Jupiter has changed from 1 year to another. You can see how it was in 2020. This is, by the way, called as the Great Red Spot, and you can see there was a cloud pattern here, and then there is a kind of an eyelid which has appeared, and this eyelid has vanished, and now it's become thinner as time goes. So every pattern of the movement of the clouds or the cyclones in Jupiter is ever changing. That means that though we assume that the planet is going to be just like that, no, every year there is a change. Every time when you look at, there is a change. When you observe, you will see what is changed. So that's how you start getting to know that this planet, which has got no atmosphere of its own, it's all ammonium, methane, everything going on around in its own cyclones. It's creating some wonderful patterns, and many of these patterns still do not have any explanations today. So this is all part of the mysteries that needs to be sorted out. Unless you do observations, you don't know. That's why they sent a spacecraft, Juno, to explore Jupiter and to understand a lot many things. From this, you can do, once you understand these patterns, it can be used for aerodynamics, to understand many other things, even what we do use today. It helps a lot of those things, wind flow patterns and everything, which we use for building aircrafts and spacecrafts. Okay? So that's how we get inspired from observing all this. Next is this is a radio telescope. What is radio telescope? So we have the visual telescopes where you can see. Here we look at the objects through a kind of a grid of antennas or something of like that, an array of antennas or a parabolic antenna or something of that sort. And we observe only pulses or electric pulses. This is how a radio telescope looks like. The advantage of this is that if you have clouds and it blocks the view, you can't see the sky, you can't see the object, this object is blocked. In radio, you have none of these clouds or any such artificial barriers, be it even sometimes some trees or something. They don't interfere. The signals, radio signals, cut across and come to you. So they come and we can still observe the object of interest of ours. And this is how the radio sun looks like. The sun in the radio frequency looks like. I'm observing the chromosphere, trying to understand what is the magnetic flux density of a sun. This is an actual observational graph of that. And down below here is looking at meteors. So you can observe meteors which are flying across. And this is a radio meteor. You can observe how meteors work and what is the length that we were able to see, what was the time period. You can observe a lot of meteors. Meteor showers are a periodic activity. Even otherwise, you can observe meteors which keeps on flying across. When we have rain or clouds, it does not matter. It still picks up the meteors which have been flying over Bangalore and records it. So this is one way of doing this radio astronomy. And then you can also see some man-made objects. This is the ISS which has been captured. So this is ISS here, ISS, International Space Station. And then, so we call this as a photo bomb. What really happens is that you can just observe the picture that I'm taking. And this is a satellite which is moving in the frame. You see, the satellite is scratching across the picture's frame. And this frame is a waste for me because the satellite has ruined the frame. So sometimes they just interfere into the pictures that you're taking. Now this is a collage of stars. You can see, I'll just play the video. Each one of these stars are of different colors. Now the colors are because of, one is the star temperature. Higher the temperature, you get a bluish white tinge. Lower the temperature, you will start seeing the white stars are much more higher in temperature. Bluish white and blue stars are very high temperature stars, and the yellow orange stars are much lower in as compared to the blue stars. So if you say in the scale, say if this is 10,000 degrees Celsius, this will be somewhere around 5,000 degrees Celsius. It's still hot. It's just that they are lower in scale, in size of temperatures. Most of the time, the color of the stars are also because of the composition. Sometimes there will be a slight amount of sulfur coming. All stars are nuclear reactors where hydrogen gets converted into helium. That's the fundamental part. But there will be certain traces of certain other elements which just add to the star color, and that's how you start seeing stars of different colors apart from the temperature. You can make out what is the composition of a star using a field of study called as spectroscopy. That's another day's talk. Okay. Now, this is a constellation of Saturn, which has been traced. This is the actual picture. This is on the left side and the right side. Here you can see Saturn, all the stars, and all. So this is the Milky Way band, which is also coming out, which is part of the picture. So this is how Saturn looks in the background of a Milky Way. Okay, all these are constellation pictures. This is Orion, Taurus, Orion with the Bernard's Loop. This is a well-known constellation down below, called as the Ursa Major, or the Saptarishi Mandala, that we call it in Indian astronomy. You can see, this binary star called as Mizar and Alcor, or Vasishta Arundhati, the bigger star being Vasishta and smaller star being Arundhati. So it's just like, planets move around a larger star. Here, smaller stars move around a bigger star. That's called as binary stars. Now, we're just looking at objects which have captured. So when you start going into nebulae, nebulas are nothing but a huge mass of cloud, most of the time hydrogen. Reddish in color means it is hydrogen. And then you have this kind of, yellowish tinge that comes from the sulfur or S2 ions, sulfur 2, or the bluish tinge comes from the oxygen 3 ions, which are suspended as part of the interstellar matter. And that gives the colors to each one of these nebula. A nebula as such is a cloud, and from the cloud is where new stars are born. This is called as a stellar nursery, like this. If you see here, tiny, tiny stars, maybe if this picture was taken around 80, 90 years back, these tiny stars would have not been there. Now they have appeared. It means that stars keep coming out, or they are born most of the time through the interstellar cloud. This cloud gets crushed by gravity, and that's how you get a new star. So we'll talk about stellar evolution someday. It's a very interesting topic. This is a supernova remnant called as the Thor's helmet, where one of its stars has died and given out all the mass of the star mass is just burst out, creating this this pattern of a Thor's helmet. Okay, so these are pictures, various other pictures of nebula, and each one of these nebulas have name and everything based on the patterns that they generate. Okay, like this is a monkey face, so it's called as a monkey head nebula. Very interesting when you start reading or looking into it. Now we'll start observing galaxies. There are various types of galaxies. So this I've just given some pictures of them. One is an elliptical, there is a lenticular galaxy, there are barred spiral galaxies. Just giving some idea about how galaxies look when you take pictures. Most of the galaxies will have either one or more than one black hole in the middle of them. So these are other pictures of a galaxy. And there was a question which was asking about how the Andromeda, and when we have Andromeda and Milky Way coming together, how will it look? Or what is going to happen? You have this picture here called as interacting galaxies or galactic cannibalism. That means where one galaxy merges into another. This is here, if you see this picture, this is in the process of happening. So you can see this in the Virgo constellation, in the Virgo galaxy supercluster. So there is an area within the constellation of Virgo where you can see this. You can observe them. This is a picture that which shows that. Galaxies do come in various types and forms and everything. It's wonderful to see. So this is Andromeda galaxy. Then I think next is star clusters. Star clusters are those objects where you saw the nebulas earlier. So when you start compressing nebulas, new stars are born. One cloud gets compressed so much that a whole new set of stars are born at the same point of time. So they are called as star clusters. That means they're all born out of the same mother cloud. So these stars that way become siblings, brothers, sisters, and so on. So they come in structures like open cluster, like this, irregular, or globular cluster, where they're all clubbed more or less together in a dense mass. So it can go from anywhere to a few hundreds of stars to thousands of stars in a star cluster. So this is just a picture of the star cluster, and many, many such star clusters are there, and you can keep on observing them. This is just a collage of that. So thank you, and that's what I had today as an introduction. And these are pictures of the eclipses and so on. Yeah, most of my pictures or some part of my work is always there on the Instagram. If you have time, you can go back and take a look at them as well.
So we have few questions in the chat box.
Yeah.
Where Shrikant asked, like, what is the difference between astrology and astronomy?
Mhm. Okay, the difference is fundamentally like this. Astrology, when we start reading the original texts, okay, is called as Phala Jyotisha. Phala is always referred to as some kind of a predictive method of telling something or looking into a future event or trying to predict something. That is called as Phala. From the astronomical point of view, always it is called as Anka Jyotisha. Anka here refers to mathematics or calculations or seeing the stars or planets, where you can get all the fundamental algorithms of doing calculations. That's the basic difference between Anka Jyotisha and Phala Jyotisha. Anka Jyotisha is absolute. It means that it is always truth. Okay. So I'll just go to one small definition. So when we just go to the definition of science, this is a definition by Feynman, who is a very well-known physicist. He says that how do you define science? First is that you come with a theory, and then you compute consequences, and then you you either do through observation or through experimentation or collecting data, and then if they all match with the theory and they agree with the experiment, then it becomes proof or empirical evidence. This becomes science. So when you call it as astrology, you are trying to predict. It might occur or it might not occur. It's always given a probability and it's left to chance. Now the question would be that you call it as a science or not is left to the person rather than we trying to answer it. Okay. So what the definition of science is this?
Sir, Yamuna ma'am asked that if she was wondering if you're open to allowing visitors to your rooftop observatory.
Yeah, I can do that. We'll have to do some planning and we can do that.
Okay. So we have a few questions from the form. So can we answer it? That
Yeah.
is
Yeah.
okay. So we have our first question, which is there are ancient talks on astronomy in India, and ISRO has used some concept.
Yeah. So there are.
So
when we-
will this or any future talk address for it?
so that if we start going that in a methodical way to understand what is meant by Indian astronomy, that itself takes a series of talks. By the way, I have been doing a series of talks in association of Bangalore Amateur Astronomers. I will just let me know if you're able to see this picture here. Just sharing this. You're able to see this?
Yes.
Okay. So it starts with Indian astronomy as an introduction, and it's still going on. The series is going on. It talks about various aspects, and all of this involves practical applications with a lot of mathematics. Like when it comes to Madhava's talk on Madhava's series, it's fully about calculus. And when we start talking about celestial navigation in India, it starts a lot of trigonometry and spherical trigonometry. So all I'm trying to tell is that if we understand the subject in its true form, then we can start appreciating how it can be applied and where it can be applied. Okay. So if I don't know what point of view we are talking from the ISRO's case here, because if we are talking about measuring orbits or trying to find out orbital motions and everything, there are wonderful texts available in Indian astronomy which talks about that or gives a great description of that mathematically, which means pure science. So we can explore that. It just, yeah, as I told, yeah, if we want to continue the series, we will have to pick up a particular topic and then we can explore.
Right. So we have another question. How do we recognize the difference between stars and planet with the naked eyes and if in the at the different time of the year?
Okay, so it's very fundamentally what they also try to say is that, the planets have a much steady light than a star. Correct? When you just look at through a naked eye. So if you observe, say, even today, either a Venus or a Jupiter or something in the sky, it's got a very steady light. That means it doesn't flicker much. If it is not flickering much, you can assume that it is a planet. As you compare next to the planet, if there is a star or any other object which starts flickering much more than the object which is a planet which is having a much more steady light. That's the naked eye way of doing it.
Okay. Sir, another question. How to watch planets using telescope? I think we have covered this, I believe.
Yes.
Yeah. So we'll move on to another one. So being an amateur astronomer for more than 2 decades, won't tell you, it's just a statement that we can't, I think, yes, we can't is saying. So we'll move to another one. And the another question is, do you believe in the existence of white holes? Why?
Okay, good. So once again, I'll come back to this statement.
Okay.
The theory is that there is always existence of white holes. Like there was a theory which predicted the existence of a black hole, right? So there is also a theory which is the existence of wormholes. Now, nothing stops from a theory. It's always good to imagine. Imagination is a great way of representing things. But over a period of time, you need to collect enough data or use other methods like mathematics to have credence to that theory. And then you collect data and then you show that, okay, this is how things work, or they encounter actually a white hole or a wormhole. Then it becomes an empirical evidence, right? Otherwise, to give credence to the theory, the next part is generally going back to mathematics and seeing what is the probability in which what equations fit this theory of existence. And then you start looking for it with a signature or a trace of it.
Okay. So we have another question where Ria asked that why there is no light in space.
There is light in space. There is. That is how the sunlight reaches us. It comes through the space, right? So, travels through the photons, which carry the light packets. They are undisturbed in space, and we get them. That's how we are able to capture all the nebula photos of all the pictures of the other objects like galaxies and everything. Yeah.
Okay. We have another question. Why do the planets have different colors?
That's because of the composition of what they have as part of the planet. Like say Earth is, when you start looking at it, it's bluish in color because of the Raman effect, right?
Yes.
Okay. And the same way, when you start looking at Saturn, what happens is the rings of Saturn is dry ice. So dry ice crystals are the Saturn rings. They rub against each other, and when you rub ice against each other, what happens? It's like, polished like a mirror, And then this mirror, what it will do is that it will reflect the sunlight onto the planet itself. The planet's gases excite based on the composition of a gas, methane, ammonia, sulfur, and then it gives out a color. So the study of what gases or what composition makes either a planet or star is called a spectroscopy. So this way you can find that out. I will try to show one picture here. You see, this is a spectral analysis. That means the sunlight is coming through a tiny slit here, and you use a spectrogram or you use a spectroscope to split the sunlight, and it gives you a waveguide or spectrum. Through that, you can find out what is the composition of the sun itself. You can see this is called as hydrogen beta line, which this peak here, and the tiny peak here is a hydrogen. It's a helium line. So which means that mainly sun is composing of hydrogen, and then helium is also there because hydrogen is getting converted into helium. So you can actually split the light coming from any star or planet and find out what is the composition, chemical composition of that, and that all falls within the periodic table of elements.
Okay. We have another one. Why does stars appear yellow?
Oh yeah, I told you, it's not that it's always yellow. They are of various colors and colors. Yeah, and the colors are dependent upon the composition and the temperature.
We have another question. How does all the matter around us came?
That's after the Big Bang, and then there was. We'll have to get into a discussion for this, but in short,
A detailed one, I guess.
yes, this is how it all began.
Yeah.
Okay, there was a Big Bang, and then there was a rapid expansion, and there was a lull in between. It's a fundamental physics. We can probably get into it one discussion some other day.
Right.
Yeah.
We have another one. What are the constellations that we can see in the Bangalore sky now?
That's a nice question. So for that, I will just tell you this is Stellarium map. Are you able to see this?
Yes.
Okay. So this is the Stellarium app. Okay. Now, if you see in the east, you can see all these constellations here. See, this is Monoceros, this is Orion, this is Gemini, this is Cancer, this is Puppis, this is Canis Major. Just download this app, and then you will have to do a few settings, like you will have to tell where in the earth you are if you are in Bangalore, or all that settings, basic ones you do, and then you can. This will start giving you a picture of what all you can see at a given moment of time. Okay, and you can do all this, like you can scroll east, west, north, south, and see all the constellations that are visible at this point of time. This gives you a good hang of what you can get to see in the sky when you plan an observation session. Okay?
Yeah. We'll move to another one. We have how will galaxy look like when Andromeda and Milky Way galaxy will collide?
I showed you that picture there. I showed you an interacting galaxy picture. How it will look. Yeah, you see this interacting galaxies picture here. Yeah, this is one galaxy and this is the other one.
Another
You can
one.
imagine this. This is actually happening now in the sky. So we are talking about an event maybe a million years later.
We'll move to the next one. Why does it take millions of years for planets to come into the rare planetary organization they are currently in?
Oh, it's not like that. So they do come, as I was trying to tell you, conjunctions are quite natural, where 3 or 4 planets are seen together in a, I have taken pictures of conjunction. Let me see if I can pull something out. Okay, but they are not that rare. You can predict those events, and when whatever that is being kind of hyped today in the internet as parade of planets and all that, it's not like that. It is not that all planets are standing in a line um, in a school assembly. No, it's not. It's there on an imaginary line in the sky. Let's go to this. Let's go to this application here. Once again, I'll show you. You see this? This is Saturn here. This is Venus. Okay, they are quite far apart. If somebody wants to see Jupiter, this is Jupiter here. Okay, Mars is here. So it's not that they're all clumped together. They are spread across a large area of the sky, and you'll have to really look at them and find them to see. This imagine this is this is the east and this is the west. Now Venus and Saturn are nearer to setting almost now. It will set in a few minutes. And whereas Jupiter is still there, it's yet to come to the zenith. And has raised, and it's almost 20-30 degrees up in the horizon. So that's how it is. It's an illusion created. It's not like that, but some of the times you can see them together in the same frame or the same when you see that from a telescope or something. Two planets can be seen together. It's called as conjunctions. Okay, it's more from the point of view of the observer, but from the point of view of orbits, they are very far apart. Okay.
Right. So we'll have one last question, which is what is astronomy and why do people have knowledge about it?
Yeah, we started with that, right? What is astronomy?
Yes. Yes. So I think, yeah, please go ahead.
No, as we started with that, it's an observational science. It gave us the whole context of few fundamental things that we are using today, like measurement of time. Just imagine you did not know how to do measurement of time. There would not have been a civilization existing. We will not be seeing internet. We will not be seeing satellites. We will not be seeing television. We will not be seeing any imaginable gadget if there was no fundamental measurement of understanding how to measure time itself.
Right.
So that's why, and that's how important this subject is. And it gives you that vision and dimension and understanding of how things work in this universe. Curiosity, and it starts answering that question. It gets into the realm of science. It's wonderful.
Right. So we have come to our session ending. Much, sir, for making this session so interesting and engaging. I'm sure the students and everybody had a wonderful time. And a big thank you to everyone for joining us today. We look forward to seeing you again on 14th of February for our next exciting session. The registration link and further details will be shared with you shortly. Thanks again and have a great evening.
Thank you so much, everybody, for bearing this monologue for an hour and a half.
Thank you, sir.
Thank you, Xperimentor. Thank you, Aparna.